All right, so today we're looking at simple. The topic will be divided into two parts. This week we'll look at syntax and dynamic semantics. Next week we're going to look at static semantics and compilation and everything else. So we're going to essentially go through all the aspects that we defined for the previous language, the EPL language, right? But we're going to add to the EPL language a few new features, which will make this language actually Turing complete. So we're going to define the language and go through the dynamic semantics, right? In defining the language, we're going to define the syntax. We're going to look at preprocessing. We're going to try to understand what syntactic sugar means in this context. We're going to look at a few sample simple programs, and we're going to try to see what do we mean by abstract syntax tree, right? What do we want to add to the previous language? Conditionals, functions, and recursion, right? Is clear? So we're already in a realistic kind of framework, right? We have, we will have a Turing complete language. We can define any kind of computation, right? You are going to see some of the most important, most basic tools for implementing a language. All right, so we're going to start with defining the types, because we want to add some new type expressions. Previously we had the type int and bool, right? Now we're going to have a new type, the function type, the arrow type, right? And we're saying in that third rule that if T1 and T2 are well-defined types, then T1 arrow T2 is a well-defined type, right? With the intuition that this represents a function from type T1 to type T2. All right? So if these are the basic types for our language, right? We knew of Boolean type and int type from last week, and now we add a new construction called arrow that takes a pair of types. And don't be fooled by the arrow, right? When I first started with functional programming, which was probably around the same time as you in my first years of college, I was looking at this arrow as a very magical thing, right? Because it's the type of a computation. Actually, it's just a pair. It's just a pair syntactically written with an arrow in between, but it has two types, nothing more. All right, and in that sense, we, at the level of type level, we're going to manipulate it just as a pair. It tells us the domain and the codomain of a function. And actually, if you think of functions, right, because again, it's this magic of computation, but the semantics of a function is the set of all pairs of input-output values, right? If I take the x plus 1, right, there is a computation there, and of course I want to define it as a computation because that's the most compressed way to define the function. But if I take the pairs 0 to 1, 1 to 2, 2 to 3, the set of all that pairs, that defines the function equally well, right? I don't need to necessarily know the computation, I just need to know the mapping, right? So a function is very much like a mapping, right? And it's just a set of pairs, right? And the type has two subtypes inside, right, linked by this strange arrow syntax, but it just defines a pair. I might as well put brackets around it and a comma in between, and I don't lose anything by doing that. Cool? All right. So, arrows. Everything else remains the same. We move on into the realm of expressions, and these are rules for expressions that you know already from last time. Nothing changes, we only add on top of it, right? So we talked about this, but there are a few new types of expressions. So conditional, right? If E, E1, and E2 are correct, well-defined expressions, then so is if E, then E1, else E2, end. We're going to make it easy for the parser, right? A lot of languages do not have the then keyword. A lot of languages do not have the end keyword, which might make parsing a bit trickier, right? Here, we make it very easy for the parser. It's more work for us, the coders, when we use the language, right? But the important aspect here to learn is how to implement the language, right? So we can accept a bit more effort on the coding side. End function application, which is carried, as you can see, right? And we're going to have the brackets as being compulsory, right? So if E, E1 up to En are correct, well-defined expressions, then bracket E, E1 up to En, close bracket, is a correct expression, right? With the intuition that E evaluates to a function, right? It can be any expression, but when we evaluate it, that evaluates to a function. E1 up to En are the arguments to the function, evaluate two values that can be used as the arguments, and the entire bracket, right, means that the function is applied to its arguments, it returns a value, and that value is the result of the entire expression. Stop me to ask questions. I'm trying to push things a bit because we wasted a bit of time, so I'm trying to push things so that we can finish on time. So we saw function application, but we cannot have function application without function definition. How do we define a function, right? So again, our syntax is going to be a bit weird here, right? Very unusual, but that makes parsing easier, and we don't want to spend too much effort on creating a parser. So we're going to use the word fun for function. We're going to write the type of the function first, which is extremely unusual, right? But this is how we roll. So we're going to say that it's a function from type T1 to type T2 to type, and so on and so forth, type Tn to T. T1 up to Tn would be the types of the argument, all right? And T would be the type of the result of the function. And then we provide bindings, right, variable names for the arguments, x1 up to xn, with the understanding that x1 is supposed to have type T1, and so on and so forth, up to xn having type Tn, right? And arrow expression. Expression is an expression where x1 up to xn will appear free. We're gonna say what free is in a minute, but since you have gone through proof for a module about logical proofs, you probably know what free variables are, right? Free versus bound variables. If not, don't worry, we're going to define them, right? So I'm telling you that inside E, we should have x1 up to xn appearing free. Okay? Yes? Oh, x1 and xn must be pairwise distinct, meaning that, for instance, the symbol a cannot appear twice. I cannot define a function, right? My arguments have to be distinct names. Right? I cannot say f AAB. I cannot distinguish between the first A and the second A, right? Similarly, we're going to define recursive functions using the keyword recfun. In most languages, such a distinction between functions and recursive functions is not necessary. Again, we're going to make it easy for us. The expression E in this case can also contain the function f. Notice that in the process of defining a recursive function, we are giving that function a name. The name f, right, is supposed to be the name of the entire function, right? But we're going to see soon, right? This f is the name of the entire function only inside here, right? This expression, let's put in a different color, is not called f. So F is sort of a local symbol, right? And we're using this because we want to be able to refer to F inside E, and that would be the recursive call. Okay? Obviously, now F goes into the mix. So F alongside with x1 up to xn must be pairwise distinct, because otherwise inside E we cannot differentiate between these symbols. Yes?
What's the value in the state of separating recursive functions and non-recursive functions?
Now, it's just syntactic. So in most languages, you would be able to say something like let f equals function, right? And inside here, you can use f. But this creates a slight problem, right? Because we want, in our semantics, we were talking about preservation, if you remember last time, right? So this is one place where we wouldn't be able to ensure preservation. We want a simple way so that every expression has its own value in a self-contained way.
No, I understand.
Right?
Okay,
so if I'm allowing this, when I look at this expression, I don't know what f means, and I don't see the recursion, right? In most languages, this is not a big problem, right? In general, in practice, this is not a big problem, right? But for our theoretical treatment, this is going to be a problem, right? So I want this expression to work like an anonymous function, right? But still be recursive.
Right. What I mean is the reg fun definition, doesn't that already cover the function definition? It's an extra value that you put in the definition. But doesn't reg fun already cover everything that fun can do? Right?
Not really, because in this context, the way we define the language, f would not be allowed to appear inside E. If it's not recursive, we won't allow f to appear inside E.
Right, and that's the question, right? Does not allowing f to appear, does separating that out into two types of definitions that make parsing easier, compiling easier?
It's going to make the semantics easier.
Okay.
Yeah. Okay, but yeah, good that you pointed that out. So we're taking a shortcut in terms of making the semantics easier for us, right? Otherwise, in terms of defining preservation, I sort of tried to touch a little bit on that discussion last time about the Lego blocks. In order to create those kind of Lego blocks that sort of can be combined with each other, right? We would have to add extra mechanics that is not immediately obvious, right? And maybe at this level, it's not. There's no point in going so advanced, right? We could just accept this and find a type of semantics that sort of works better, right? The semantics would be a little bit simpler. Okay, more questions? Cool. So again, we're going to sweep under the carpet the distinction between the expressions and their syntactic trees. We're going to assume that these two constructions are perfectly equivalent. All right. In general, we're not going to we're going to deviate from the typical associativity of operators, right? Operators typically have precedence, and most of them are associative from left to right. But here we're going to, we're going to assume that, but if there's no brackets, we're just going to perform them in order, right? So x plus x. Oh no, actually we do have precedence. I have to look at the parser that we use. There might be precedence in there. My impression was that that we wouldn't be implementing precedence just for simplicity. But this is again not a big deal, because we can always use parentheses to change the precedence of the operators, right? So the fact that whether we implement or not precedence correctly, we can always go around that. The arrow is an operator, right? And we're not gonna touch very much on that aspect, right? What we are building for types is type expressions. There's an expression language for types, right? And OCaml, as well as most functional languages, have that developed into a mini language that is very useful for writing DSLs. And hopefully when we get to the point of writing DSLs, we're going to dig a little bit more into this aspect, right? But think of the type expressions as expressions that are joined by operators. The arrow is an operator. You can think of it, right? And then it associates to the right. It is very important because whenever you see expressions like int to int to int, right, you need to assume this, meaning that this is the type of a function that takes one argument, right? When I write f12, right, what we mean is that this function takes one argument, so is this application here, and that returns a result which is a function. That function takes another argument and returns a result, right? And at the compiler level, this never happens. It never happens like that, right? Building what we call a closure, a partially applied function, is too expensive. Compilers try to optimize these kind of applications as much as they can, and actually will uncurry all the functions. We'll transform them into function taking tuples as arguments, right? But for the theoretical treatment, this is very useful, and for building a semantics, again, this is very useful. So we're going to stick with this convention. It also allows very beautiful type constructions to be built if you, for instance, build libraries. So when we talk about DSLs, perhaps we're going to dig more into that. So this is an expression of a correct expression in our language, right? It defines a function that takes one argument x, right? And which returns a function which further takes an argument y and adds the two arguments x plus y. Okay? So you can sort of see that this part, right, this part is a function with one argument that returns a function, right? So the type of x is this int, and then what we return is the type of a function, right? And now if we dig inside further, we're seeing that we're returning a function. So these two types, let me change the color. These two types need to be the same, all right? So at that point, we can dig in and check that this there's one argument here which should have this type, and then inside this expression at this level, we have two bindings: one for x, which is at the outer level, and one for y, and both of them can be used inside here, right? It also shows, yes.
Yeah, I'm just wondering. So all functions in this language are anonymously defined, right? Except for the recursive.
Well, no, even the recursive function, right? So the f that you are defining, that you're using, is sort of an argument to the rec fun, if you understand what I'm saying.
But is there a reason why we're not giving functions names just as yet?
No. So we're defining a base language. We're going to introduce the let in very shortly. But let is just syntactic sugar, right? Okay. So to be Turing complete, you don't really need naming, right? Naming is a matter of convenience. So just having a ability to build anonymous functions is good enough to have Turing completeness, right? You won't get very readable programs, but you don't lose the power of Turing completeness. Yeah, so we're going to have let. Just be a bit patient. Okay. So another one, right, where we might want to associate the types differently. And if we want to associate them differently, obviously we have to use explicit brackets. Here, we didn't have to use explicit brackets. We could have put brackets here, right? But they're not necessary because the natural association of the arrow is to the right. But here we do have to do that, right? So here we're saying something different. This is a function that takes a function as the first argument and returns an int, right? So then this f has this type, And then what can we do with that f? Since it's a function, we can apply it to some integer, and right, this expression must have this type, right? Therefore, right, the type is correct. So we can have functions as first-class citizens. We can have functions as arguments. It's okay? Cool. Now, there's a notion of syntactic sugar. Most languages are defined in the following way. First, we define a core language, which we pretty much have done already. And then they define what they call syntactic sugar. So more complex constructs which, however, can be reduced to the core language, right? And then in processing that language, the first phase is pre-processing, where all syntactic sugar constructs or definitions are translated into their core counterpart, and then the compiler works on the core language. All right, and there are many very familiar constructs that will may be surprising to you, will be defined as syntactic sugar. And the most common one for functional languages is the let, right? We're defining names for expressions, right, which make, in general, programs more readable. Why do we need names? So if you haven't figured that out, there's two reasons. One, expressions can get very large, so you don't want to, and expressions sit well on a single line, right? So you don't want to have to write very long expressions. You would take some expressions, name them somehow, and use the names instead, right? The other thing is that it is nowadays standard software engineering practice to make the names as self-descriptive as possible, right? As descriptive as possible, and they become a way to document the code, right? You don't document the code in comments anymore. You try to make it as readable by giving appropriate names to functions and variables, right? So if you look at professionally written code, you will see these very long identifiers in camel case, right? Each variable saying what it contains. Variable names like I and J and X, they're not in high favor anymore. All right, so let's look at the syntax here. It's very similar to what you know from OCaml, just that we write the type next to the variable or before the variable all the time, right? Why? Because doing type inference is quite difficult. Actually, not that difficult, but maybe it's not how you want to introduce a class on types in programming languages, right? So what we're going to do is type checking. We're going to ask the coder the user to write all the types, and then we're going to have the compiler check those types. Actually, this is quite standard practice. If you look at languages like Java and C#, there is no type inference. Actually, C# has some type inference in more recent versions, right? C# 5.0 has this var. You can define a variable without giving it a type, and then the type would be inferred from whatever the assignment is there. But functional languages typically do have inference, meaning that you're not required to provide the types. OCaml has type inference. You're not required to provide the types. The types can be inferred from you from constants and predefined functions and so on, right? But in our case, we will require the types to be written explicitly because it's easier to check than to infer, right? So let's figure out what we mean here by syntactic sugar. We have this let expression, right? x1 up to xn become new names that we can use in the expression e, which is potentially a large expression, right? And you notice that all it means is a function application. I can always put a function definition around e, right? and pass the expressions as argument. So it's pretty clear that the two expressions perform the same computation, right? The second one in real life would probably be a lot more difficult to read, right? Because you'd be seeing the x1s inside the t here, inside the e here, sorry, x1s up to xn's without knowing what they mean, whereas in the let format, you would see the definitions first and then the use of the definitions, right? The functional abstraction would show you the use of the definitions, the use of the variables first, and then their definitions, which is probably the wrong order. Is this clear? So whenever we encounter a functional program, right, the first thing we do is this preprocessing phase, where every let expression gets transformed into its functional abstraction form, and only then the compiler goes into action. Functional partial application, right? So I was telling you that so we can do this, right? We can have a function f that has perhaps 3 arguments, right? So normally I would use f and apply it to E1, E2, E3, right? But because of this current format, and because of the fact that I can think of f as a function that takes an argument of type T2 and returns a function that takes an argument of, sorry, I said T2, right? So f is a function that takes an argument of type T1 and returns a function that takes an argument of type T2, right? And returns a function that takes an argument of type T3 and finally returns the result of type T4, right? So actually we can think of it as 3 tiers, right? I take f, I apply it to T1, I get a function that gets an argument of type T2, and that application returns a result, which is a function, right, that takes an argument of type T3 and returns a result, which is actually of type T4. So at that point we get. So if I apply a function only to 2 arguments, right, I should get a function that is ready to accept the remaining arguments, right? So an expression like this should return this type, right? And we can easily perform this translation, right? Look at this function, all the more that internally at the compiler level, this compiler will expect E1, E2, E3, will expect the tuple. It's extremely inefficient to perform the computation that I just described, so it will be optimized under the carpet. So whenever I have a partially applied function, it will be converted into something like this, right? The compiler will always want to see all the arguments to the function because it doesn't like, it's not really that it doesn't like, right? So producing what we call a closure, which is what the value of a function is, that's expensive. So that's to be avoided at all points. So it will perform this kind of syntactic sugar, and it will translate partial evaluations into new function definitions, right? So that closures can be avoided. All right, so typically what we do is we perform a preprocessor step. And how do we do that? Well, we take the abstract syntax tree that the parser provides to us, and we take all types of expressions, and we try to perform recursive reductions of syntactic sugar, recursive translations of syntactic sugar, and use those, right? So obviously there's nothing to do for a Boolean constant or an int constant or a variable, right? Whatever the expression is, since it's a constant, there's nothing to do there. But if I have a unary primary application, so a unary operator, in this arg, I might have an inner let, right? So then I want to recursively go and remove that let, translate that let, right? So I'm going to do this, I'm going to get this translated varg, and I'm going to use that varg here. That varg is something that doesn't have let, and that also doesn't have partially applied functions, right? So it is a recursive function. If I have a conditional, right, and this is how the if will be translated into the abstract syntax tree, right? I would have a conditional with the condition here, the consequent, and the alternative, right? If then else. And each of these expressions can contain either a let or a partial application, right? So what we're going to do is recursively remove those, right? So I would get v1, v2, v3, which are the equivalent expressions without the syntactic sugar, and then I will use those in here, right? And so on and so forth. So it's simply a traversal of the tree whereby, right, whenever I see an expression that is potentially complex, I will perform the removal of the syntactic sugar. So after applying a step like this, and you're going to see it in the first homework, this function will be there, so you can look at it more closely. When you do that, right, we obtain a program that is in the core language. Okay? So let's look at an example. Let's say this is the program at hand. We have a let, and we want this removed, right? We want this translated into a non-syntactic sugar form, right? And this is it. Okay? So let's very quickly look at what's happening here, right? We have two variables, 3 about pi, which is 3, which is right, close enough to 3.14. We can say it's about pi, and then we have this, right? And then this is our function. So you see about pi appearing here and square appearing here, right? So this blue expression is going to become a function definition with the arguments about pi and square, and that function will be applied to the definition of about pi and the definition of square. And this is what happens here, right? So notice that we simply, so this is the old function expression, right? Which was the body of the let. The body of the let is there, right? Then we added these arguments in front of the body of the let, and then because of that, this thing has become a function. And then I apply this function to 3, which is the value defined for about pi, and this entire function, which is the value defined for square. And this is the equivalent non-syntactic sugar expression, the core language expression, corresponding to the one on the previous line. Is this clear? All right. So, for instance, an interesting syntactic sugar, an interesting exercise would be to enhance the language with syntactic sugar expressions. So, for instance, an interesting exercise is to add a while expression, right? So you can use a while expression that has a predicate and applies a function as long as the predicate holds on a list, right? So yeah, that would be an interesting exercise. Maybe I'll add something like that in one of the homeworks. I'm not sure it is. When I learned Scheme, which was my first functional language, there's a famous book, and I learned it from this famous book. It has as the last chapter a meta-circular interpreter, right? So you define a interpreter of Scheme in Scheme. Scheme is a simplification of Lisp. There were these guys in MIT didn't like Lisp. I mean, they thought Lisp went out of control, right? So they produced their own version of Lisp, which they called Scheme, and then they used it to teach computer programming, introduction to programming for about 20 years in MIT. The book is online, available online. It's called Structure and Interpretation of Computer Programs, SICP. If you just Google SICP, you'll get there. So the interesting exercise there was always to produce as much stuff as syntactic sugar, right? Because then you could use the core compiler to simply have those features available. That was a very fun way of expanding the language. Okay, recursive methods. There's a bit more theory about here, which we're sweeping under the carpet. Does anyone know the meaning of a fixed point? What a fixed point is? All right. Let me hint at the theory. Right. So let's take a function from reals to reals. Right. So there's some function f. All right, and I'm asking you to find the solution to the equation fx equals x. Okay, which graphically is very simple, right? We draw the first bisecting line, and I want to find this intersection, right? So if this function is very unwieldy, if it's a polynomial, usually it's very easy to find an exact solution, an algebraic solution, right? But if it's, for instance, an exponential, some form of an exponential, you won't have an algebraic solution. So what you do is, typically you find a point to start from, right? And you perform an iteration like this. Okay? Which will never reach the point, but will get as close as you want. Obviously, you want to have a single fixed point, so the fixed points are not guaranteed to be unique, right? You want this function to have it's different if you go from if it's concave or convex, this function, right? So you're not always guaranteed to find a solution this way, but the process is very simple, right? Because you start from a point x0, which you pick. Typically it's random, and what you do is x1 equals f x0, x2 equals f x1, right? And so on and so forth. Xn is defined as f of x n minus 1. Okay? So it's a very simple iterative process that will take you as close to the solution as you want. Okay? Now, let's talk about recursive functions. So, when I define a function, and I'm going to use a sort of a mathematical language, and I'm going to define factorial, right? So I'm going to say fn is equal to 1 for n equals 0, and n times f n minus 1 otherwise. Okay? So we look at this as a definition, but could it be that it's actually an equation? Right, so I have this function, capital F, that takes small f, and all right, so I'm not going to put n inside. I'm going to say equals, and I'm going to say lambda n. You all know what lambda is, right? 1, n equals 0, right? And n times f applied to n minus 1 otherwise. So looking at this thing, might it be the case that I'm trying to solve f equals f applied to small f? might it be possible that we're trying to solve a fixed point equation? Okay? Yeah? Okay, so the resolver for the fixed point equation is an operator called the fixed point operator, typically denoted by mu in lambda calculus, right? So we're going to say that f equals mu f. So let's call this all right. Let's say that g, which is my factorial function, is mu capital F, right? So I take this function that is a function of another function, and I have this operator which automatically finds me the solution to this equation. All right? I'm trying to find a small f that satisfies this equation. Now, the same process that you've seen previously works here, right? But we have to we have to figure out what are the approximations, right? So I'm never going to find the exact g. That's the interesting thing. I'm going to find approximations of g, but approximations that are good enough for my purpose. So what is the space of approximations for f? Well, I'm gonna use the following space. So I have the function that which for 0 returns bottom. Bottom stands for undefined, right? So we're enriching our space of values with a value undefined. 1, undefined, and so on and so forth, right? So this is the worst possible approximation. Now, if I'm changing this to 1, this is a better approximation, right? So let's call this, the first one, G0. And then G1 is the one where the value for 0 is defined, right? G2, so we have one value defined. G2 is one where this one is defined as well, right? G3 is the one where we have 3 values defined, right? So we have the precision increase in how many, in my domain, how many values I have defined, right? So now, I'm going to have to erase this because, so now if you think of these G1, G2, G3, right? I'm looking for the solution to my equation, right? I'm looking for the G, which is F, which is mu F, right? Which is mu F, right? And it's the solution to the equation F equals F applied to F, right? So I'm going to start with G0 as the first approximation. Then I'm going to compute G1 equals F G0. What is this value? Well, it's lambda n, right? If it's 1 if n equals 0, and it's G0 of n minus 1 times n, right? Otherwise. So how many values do we define for G1? Well, I have at least one value defined here, right? G0 is defined for nothing. So whenever I get values greater than n, this is undefined, but it's at least defined for one value, right? So it's correct to say that FG0 is G1, right? Then G2 is F G1, right? Which is lambda n is 1 for n defined as 0, right? And this time, I said G0 here, G1 n minus 1, right? Times n. So for how many values is G2 defined? Well, it's defined for n equals 0. And we know that G1 is defined for n equals 0 as well, right? So when n is 1, n minus 1 is 0, G1 applied to this is defined, times n is also defined. So then we have 2 values defined, right? Yes? N minus 1, sorry. Okay, let me correct it in blue. This is n minus 1. So we have 2 values defined right now,
Yeah,
right?
And that's G1, right?
Yes, G1, which we have defined here. So what if I want factorial of 100? right? What I want to compute actually from a practical point of view, I want to compute factorial of 100. Well, I would need G101 here, right? But G101 can be easily computed as this chain, right? So in the process of, in recursion, what we have is a process of computing approximations of the function until we get a function that is defined for the value that we want, at which point we can stop, right? You never really have the function that gets you all the factorials, right? You compute 100 factorials. Semantically, what happens is you compute the approximation that is defined in the first 100 values, and then, right? And then you use that approximation. You need 1,000 factorial. Yes?
It's kind of like a dynamic programming, but without actually like storing the
This is more of a semantics argument. It's not. Why would you compare it with dynamic programming?
well, it's like you are like taking a preset until you want to find a value.
I think that's because dynamic programming is based on recursion in one of the
Yeah, so dynamic.
definition for
Okay, so there is a similarity in concept there because in dynamic programming you don't know upfront how much you're going to need to compute, right? So what you're typically doing is you're computing until you get enough values to, right, get your compute your desired value. If you think of the Pascal triangle, right, and you would use dynamic programming for efficiency there. It's pretty much you don't know upfront how much your cache is going to be, right? But you're going to compute and try to on demand fill up your cache up to the point when you have everything you need to compute your final value. Yeah, so it's something like that. So whenever we define recursion, right, we want to compute. The fixed point operator of a function, right? But let's think of what that function is. So let me wipe this again. And so let me write again. This f has an f here and has a lambda n, right? Well, this doesn't matter that much. N equals 0. 1 if n equals 0 and n times blah blah blah, right? But there's an f here, f applied to n minus 1, right? If n is greater than 0. So we're computing the fixed point of a function that has an argument, right? So my rec fun, and this we typically denote as mu f, right? But if I were to say what f is, right, I could say that this f is lambda f in front, right? So when I say rec fun, this is like the mu. And then inside here I have to say this function, but this function is defined in terms of an f here. So I have to say what that f is. This is the underlying reason for using rec fun and the way it is defined. Right? So think of this. I am going to find the fixed point operator, the fixed point function of this big F. But this big F has a small f as argument, right? Does it make sense? Okay, if you ever get to the point of okay, let's try to use it on this example because we use power, right? So normally in a different language you would say power of A and B is equal to something, and there's a recursive call to power here, right? So think of this as an equation, right? So now I'm going to take this function, this expression, but this expression is a function where the first argument would be the power symbol. And I say I want the fixed point of that. So I want the fixed point of that, right? Big F, whose first argument is power, and it has two more arguments, x and y. And this is the reason for the syntax. Cool? One thing you might want to check out if you're savvy coders is the fixed point operator in the lambda calculus. And so that's point one. Point two, on Rosetta code, you will have all the languages for which the fixed point operator is implementable. It's not implementable in all languages because it's not well typed in all typing systems, right? But it is in many, and try to understand how that works. So take a language like OCaml. Actually, because the class is almost over, so I think we're going to stop here. So let's end on that note. Yes, I'll be done. I'll be done in a minute. All right, there's a search here, fixed point. Or maybe it's fixed point. I don't know, maybe it's not on Rosetta code. Oh, Y Combinator. Yeah, that's the other name of the fixed point of combinator. Church, who discovered it, called it the Y Combinator. So here you have all the languages, and I'm sure OCaml is somewhere. All right. So this will be the definition. The definition is really simple, right? And then look at how you would define, for instance, factorial, right? So this is the big F. This is the big F that we're talking about. And then you're taking the fixed definition that is given here, and this is your way of computing factorial of 5, right? So understanding this, I mean, you don't have to do it for this course, but it's this kind of thing appears in programming interviews in places like Google and quite frequently, right? So if you want to be that level, probably this is one thing you want to look at least once in your life. Okay, let's stop here. Sorry about the delay. Sorry about the delay. Yeah, my motorbike broke down, but I mean, in the end, it wasn't a bad thing because it was raining cats and dogs, and I had trouble finding a cab.